Hello, class. Sorry about the whole power outage thing. It definitely wasn't pleasant with the heat, but I had no power, so it was kind of impossible to be able to hold a Zoom for you guys. Enough with that. Let me go ahead and talk about the dot product from chapter 12, section 3. And what the dot product is, it ends up being a scalar. So it's two vectors that are multiplied, and it gives us a scalar number for the result. So if we have two vectors, a vector A and a vector B, the dot product of A and B is this number that's given by using this formula right here. Okay, so this is an example that I have here for a vector with three in 3 dimensions. The example that I'm going to do is a 2-dimensional one. The process is one and the same. So if I have a vector 3, 4 and a vector 5, 7, and I do the dot product to them, the result of that is going to be this. So I'm going to take the 3 from the first vector times the 5 from the second vector, and then add them, multiply, and then add the second value in the first vector and multiply it with the second value in the second vector. So that's going to give me 15 times 28, and so the result ends up being a scalar of 43. Some rules for the dot product, just so you guys know. If we're given 3 vectors, and please note this right here is a scalar, it's not a vector. So the dot product of a vector itself is the magnitude squared. So this first one here, remember that this symbol here is representation, right? Which was the square root of the numbers in the vector, each squared and then added up. Well, when we get rid of that, when we get rid of the square root by squaring, we end up with the dot product of the vector itself. Just so you guys could understand it. So if I had a scalar of A, and let's say that A was that 3, 4 vector, the representation tells us to go 3 squared plus 4 squared, right? But the dot product of itself ends up being the number without the root. So this would be 9 plus 16 is 25. And so the dot product of itself would end up being that 25, where the scalar here would be 5. Okay? That's an example of property number 1. Property number 2 is showing us that if I have 2 vectors and I take their dot product, it doesn't matter which way I take the dot product, I'm going to get the same thing. So A dot B is equal to B dot A. Those scalars are going to be one and the same. If I have 3 vectors with 2 vectors being added, it works like the distribution property. So it's going to be A dot the vector B plus A dot the vector C. So it ends up being 2 dot products that are done there, again giving us a dot product. Here we can see that this is a scalar times a vector dotted with another vector. We can change this to have the 2 vectors have the dot product and then multiplied by the scalar, or we can even say that the scalar multiplies with the second vector before you do the dot product with the first. So what it's saying basically, in essence, for number 4, that the scalar can multiply with either one of the vectors before you do the dot product. And then the 5th point for it is a 0 vector dotted with any vector is going to end up with a 0 vector. Okay? All right. So then here, it's a quick theorem that we're going to have, and the theorem tells us that if theta is an angle between the vectors A and B, then what we end up with is something like this. We're going to end up with A dot B is equal to the representation of A times the representation of B, or you can call them the magnitude of A times the magnitude of B, times cosine of the angle. So if we wanted to find the angle in between these, we could do it quite easily. All I'd have to do is take A dot B and divide it by the magnitude of A and the magnitude of B multiplied, and that could give me the cosine angle. I'll do a problem like that for you guys so you can find the angle, but this is the formula that you'll need to know, and so I wanted to write it down so you would know it. So this is the formula that we use to go ahead and find angles. Okay, so if I give you two vectors and I have the lengths being 5 and 8 respectively with an angle of pi over 3 between the two angles, how do we find the dot product form? Well, one thing that we need to know is that the length is the same as the representation, right? It's the magnitude. So we know the magnitude of A and we know the magnitude of B, and we have the angle. So what we can say is A dot B is going to be 5 times 8 times the cosine of pi over 3. And so A dot B is 40 times cosine of pi over 3 is 1/2. And so A dot B is this scalar 20. Okay? There's a corollary that will come from this, which I kind of already alluded to, and this is it here. If you want to just get the angle, we know that the dot product of the two vectors divided by the product of the scalars, the product of the magnitudes will give us the cosine of the angle. So I want to show you that real quick in an example just so you guys can see it. So if I want to find the magnitude of vector A, it's going to be the square root of 2 squared plus 2 squared plus a negative 1 squared. And that's going to give me square root of 4 plus 4 plus 1, which will give me the square root of 9, which is in fact 3. Now, doing the same thing to find the magnitude of B, I'm going to get 5 squared plus a negative 3 squared plus 2 squared, and that's going to give me 25 plus 9 plus 4, and what's that? 29, 38. So it's the square root of 38. And then we also need to find the dot product of the two vectors. So A dot B is going to be 2 times 5 plus 2 times a negative 3 plus a negative 1 times 2. How I got those numbers, just in case some of you don't see it, I'm going 2 times 5, so the first terms of each vector, plus the second term of each vector, the products, plus the third term of each of the vector multiplied. And so what that's going to give me is, 10 minus 6 minus 2, which will give me, I believe that's 2. And so to find the angle between vector A and B, I'm going to go cosine theta of the dot product over the product of the two magnitudes. So it's going to be 3 times square root of radical 38. But to clean that up, I'm going to go theta is cosine inverse of 2 3 root 38. And then depending on how you want to do it, if you want to get it in radians, it would have been 1.46 radians. If you do it in degrees, which some people will prefer degrees, it'd be 83.79 degrees. Typically, you guys probably understand degrees better than you do radians. So it's just under 90 degrees, the angle between these two vectors. It's kind of important for you guys to be able to find the angle between two vectors using this method. Later on, I'm going to show you how to find it using sine also. That'll be in 12.4. But this is a method that you can use. Both will work. All right, something important here too. Two vectors are said to be orthogonal. You may have heard it from your Calc 1 teacher. I hope you did. I know with my Calc 1 class, I always talk about orthogonal. All orthogonal means is perpendicular. So that's the same as being perpendicular. But for some reason in math, we use orthogonal more than perpendicular. And we know that two vectors are perpendicular if their dot product is 0. So it's if and only if their dot product is 0 that we end up with perpendicular vectors. So there'll be questions I'm sure that will come up in the homework where you're going to have to be able to demonstrate that two vectors are perpendicular, and the way you do that is by showing that their dot product is 0. All right. Now, directional angles and directional cosines are actually pretty cool. So to be able to find directional angles, it's important that you guys get what this is. So there's going to be 3 formulas that you're going to use. It's going to be cosine of alpha. And cosine of alpha is going to relate to the vector A times I over the magnitude of A times the magnitude of I. Now, one of the things I should talk about real quick, because you may not know this yet, if you have the X, Y, and Z coordinates, the I is a vector along the x-axis that has a length of 1. It's called a unit vector of 1. The J is going along the y coordinate, and then we have a 1 here for, it's going to be K, that's going to go along the z-axis. So I, J, K relates to x, y, z, but they're unit vectors that have a length of 1. So you guys know. So when I'm doing this, I'm telling you that the I vector is 1, 0, 0. And so its magnitude is 1. So what ends up happening there, and I should put a subscript of 1 there, it's going to be I1 over the magnitude of A. Cosine of beta, that angle is going to correlate with the J, and so that's going to be A2 over the magnitude of A. And then cosine of gamma is going to be equal to the third coordinate of the vector with the magnitude of A. So gamma is referring to the angle of the vector to the z coordinate. Beta is referring to the angle that's created from the vector to the y coordinate, or the y axis, I'm sorry. And then the alpha is the angle that's created from the vector to the x axis. Okay, so that's important for you guys to know that. It's going to each of the axes, the angles it's created. And so since we're in 3-dimensional space now, we have vectors that have angle references to the x-axis, the y-axis, and the z-axis. And this is how we find those with these directional angles. So this problem right here, we have a vector 1, 2, 3. And so to find the 3 angles that create this vector, we need to be able to use these formulas. And so I need to find the magnitude of A. The magnitude of A is going to be 1 squared plus 2 squared plus 3 squared. So that's going to be, what is that? 1, 4, and 9. So I believe that's 14. Square root of 14. So we know that that is the magnitude. So then cosine alpha is going to be the first coordinate in the vector, which is the 1, over the 14, or square root of 14. And then to find alpha, that's going to be cosine inverse of 1 over the root of 14. So alpha is going to be approximately 74.5 degrees from the x-axis to where the actual vector is. Okay? To find cosine beta, remember again, this is in reference to now the y-axis, right? So it's going to be the 2 over the root of 14. So then beta is going to be cosine inverse of 2 over root 14. Cosine beta of that is going to give me approximately an angle of 57.7 degrees. And that's the angle that's created from the y-axis to where the actual vector is. And then cosine of gamma is going to be the 3 over the root of 14. And so gamma is going to be cosine inverse of 3 over root 14. I should put parentheses. And so that's going to give me a gamma that's going to be approximately 36.7 degrees. And again, this one now is to the angle referenced with the z-axis, okay? Yeah. So these are the 3 angles, the directional angles that are formed based off of the vertex, or based off of where the angles are formed of the vector to the axes x, y, and z. Okay. Now we're going to talk about some projections. And what these projections are, it's important. What it does for us, really the first one that we should talk about is the scalar projection, because the scalar projection is exactly that. It's a scalar. So this is just going to be a number, where the vector projection is a vector that's the result. So I want to demonstrate that for you real quick. So if I have this is vector B, let's say this is vector A, make sure they hit right. What's going to end up happening here is if I draw a perpendicular line dropping down there, in fact, let me do this in a different color so you guys can see. Part of vector A is this vector from A to the perpendicular end terminal point of B. That blue vector there is the projection vector of B onto A. So this is the projection of B onto A. It's that blue there. Now, that blue is still part of vector A. It's a portion of vector A, but it is, that's what the projection is. Some people will call it the shadow of vector B, but it's not quite. It's a little bit, it seems to me like it would be a little bit smaller. Now the scalar, what the scalar is is it's the length, and I'll write that down just so you guys know. The scalar projection is just the length of the vector projection. So it's the scalar projection is just the length of the vector projection. Okay, so really it's how long is that blue vector? That's what the scalar projection is going to be. And so when we do these problems, you can see that the projection vector actually has the scalar projection as part of its formula. So I'm going to show you guys how to find this and then show you how it's part of the other. So if I go after the scalar projection, one of the things that I should do is I'm going to go find the magnitude of I'm going to find the magnitude of A. So the magnitude of A is going to be negative 2 squared plus 3 squared plus 1 squared. And that's going to give me 4 plus 9 plus 1 rooted, which is the root of 14. And so when I do this here, it's going to be the scalar projection of B onto A. It's the dot product, right, of A and B. So the dot product of A and B is simply going to be the multiplication of the two vectors. So it's negative 2 times 1 plus 3 times 1 plus 1 times 2 all over the magnitude of the vector A. And that's a square root of 14. So we can see that this ends up being negative 2 plus 3 plus 2 over the square root of 14. Or that ends up being 3 over the square root of 14. Now, something that's kind of cool to see, this top number 3 is the value of A dot B. And I know that this denominator here, which we already did it up above, but I just want to point it out, is the scalar, or not the scalar, is the magnitude of A. So when I go to do the projection, right, the vector projection, what's going to happen here is it's going to be we see that it's A dot B over the magnitude of A squared times A. But don't we already have the top number, right? So the projection of B onto A dot B was 3. The magnitude of A was root of 14, but they want us to square it. And then we want to multiply it with the vector A. Well, with the vector A was negative 2, 3, and 1. And so what we end up getting is 3 over 14, negative 2, 3, and 1. And then from there it's going to be a negative 6 over 14, 9 over 14, and 3 over 14. And then we see clear as day that this is the vector. It's not a scalar, where the scalar projection was simply that, a scalar. This is the dot product. So if you have any questions on this, by all means, please ask. It's so different to teach without you guys here. And I'm sure I went kind of fast. So please watch the video again as you need. And then if you have questions, feel free to email me and I'll help you as it's needed. Okay? All right. Good luck.